Well, now it's time to start the course off. This is Lecture 1. It's going to be an overall introduction to the course. And the first lecture will be very high level. There won't be an awful lot of math in it. And it will give you just a very quick, broad overview of radar and the material we're going to cover in the course. Then, as I said earlier, there'll be 2 lectures that will review certain material in electromagnetism and systems and signal processing, digital signal processing, that are extremely important and they'll be used in the course, those concepts. And then we'll dig into the heart of the material starting with Lecture 4. And that heart of the material is going to be lectures 4 through 17, which I call the core material of the course. Okay, so let's start off with the introduction. The introduction will be divided up into 3 parts: background material, the basics of radar, and then the course overview. Now, this is the material that we're going to discuss in the background. We're going to go over some pre-radar history of how people used what target detection methods were used before radar. We're going to talk about how radar works in one simple view graph, so you can say, oh, now let's go on. And then we're going to talk about the early days of radar, how it was invented, why it was invented. And to stimulate and motivate you as students, I want to point out 2 examples from World War II, when radar was first developed for operational use, that made really big differences in the outcome, both from strategic and tactical points of view. And I'll bring in some first-hand knowledge that I have of people who actually participated in those things, and also a lot of historical reading that I've done, reporting on that material. And you'll see, wow, radars really made a difference in that war. And these are only 2 examples. I could probably, and I will name off quickly, half a dozen others that I could talk for an hour or 2 on. And then we'll go into the other subjects. Now let's start off with some pre-radar history. Well, if you think about war, it's all about knowing what the enemy's going to do ahead of time, knowing what the enemy is doing, and being able to counter the enemy and see how well your attack is doing, the difficulties it's having. It's surveillance of the battlefield, reconnaissance of the battlefield, what we call today situational awareness, understanding what's going on. And I think it was General Eisenhower who said, before war, plans are everything, but once a war starts, throw out the plans. That's my interpretation of those words. You know, it's about what he said. And that's what happened, of course, at Omaha Beach and D-Day. They thought they'd be many miles inland, and they had a very brutal, hard time on Omaha Beach at D-Day in World War II, getting ashore for a large number of reasons. And on Iwo Jima, there was just no way that they had of knowing how entrenched that the Japanese were, as you can see there on the island of Iwo Jima, in Mount Suribachi, and how difficult and devastating the attack would be. And so the less uncertainty there is, the better you like it if you're a commander of war for your troops and for the outcome of the battle. Now, before radar, a lot of different sensors were used to detect aircraft and to detect attacks from the air and the ground, for that matter. Here we're focusing on air attacks. Optical systems were used quite a bit. Searchlights were used in the 30s and 20s. And you can see here This is actually around Gibraltar. It's a photograph courtesy of Great Britain. A lot of the World War II photography that was taken by the British government has passed the copyright age, which is somewhere up in the 40s or 50s of years, and it's now all in the public domain. This particular photograph is was taken by the British government. And here's another one from the National Archives. Just a plain old fellow on top of a building with binoculars. Here's, I think, St. Paul's Cathedral in London. But the optical systems have some significant problems. There's attenuation by the atmosphere, and there's significant range limitations. And because of the nature of the wavelengths, you can see there are very narrow fields of view. It's hard to see over a wide field of view, and that's caused by, as we'll see later on, caused by the very small wavelength that optical radiation is. And then there's the issue of cloud cover. Light won't allow you to see through cloud cover, and worldwide, 40 to 80% of the time, things are covered with if you look up at a certain point in the sky, there's clouds in the way of where you want to see. To give you a worldwide view of that, this is a NASA photo of a study that was done over a period of many years in the 1980s, looking at total cloud cover in the world. And you can see that a very large portion of the time, here's the percentage of the time that the radiation's opaque to cloud cover. And, excuse me, this is the percentage of the time that you have cloud cover. And you can see that it just, there's not a lot of the time that you have cloud-free line of sight that you can count on. And both infrared radiation and optical radiation are opaque to clouds. Now, people also use sound. If you live near an airport, hopefully not too near, and you can hear a jet plane that's 25, 30,000 feet up in the air. Where I live, it's near a major air base, and not too near, but when jet planes are flying 30,000 feet above, you can easily see them, and if you're driving even several miles from the airport, you can hear them coming. And in the first half of the 20th century, the military of many nations, the Japanese, many European nations, here are two U.S. Army acoustic detection systems, developed systems that, again, were limited in range. The sound doesn't travel that far, even from a very noisy jet plane. You know how loud it is when you get up, enter a jet plane and the jets are idling even. It's extremely loud, but more than 10, 15 miles away, you really can't hear them. And so the range is quite limited. And again, these are directional sensors, and the ambient background of weather, lightning, storms, wind in the trees that's nearby, all contribute to limiting the range. And these were used in the first half of the 20th century along with searchlights at night. You notice, particularly in these systems, it's easy to see that there was sort of an antenna listening above and below, and from an operator over here with earphones measuring if this signal was higher than that signal, they knew that they weren't pointing exactly at the angle of the planes, and so they could adjust on azimuth or elevation the instrument and get the right directionality of where the aircraft or group of aircraft were coming from. Over in Great Britain, just before World War II, the British got quite serious because this is what they saw as, gee, this is all we've got. And they built huge sound mirrors. And this is in Kent, in the UK. These are the remnants of sound mirrors that were built a short time before World War II. And even with a 200-foot parabolic receiving aperture where an operator would sit at the foci of the parabola or at these here, the operator would sit right there at the focus with earphones listening out, the detection range was less than 15 miles. Now, even during World War I, if you could hear a British Zeppelin, like a blimp, 15 miles away, it was only moving 10, 15, 20, 30 knots. It would give you some warning. But with faster World War II German bombers, these kinds of technologies just wouldn't cut it at all. This shows you how radar works. It's really simple, you know. A pulse of electromagnetic radiation is transmitted by the radar. It's given directionality by an antenna. And of course, each of these words I use, like directionality of an antenna, there's going to be a whole giant lecture on each of these pieces. The electromagnetic energy will hit a target and scatter off of it. Some of the energy with a different color will scatter back out in all different directions, but some of it will go back to the antenna. It will be received, listened to, and the difference in the time it takes, the round-trip time it takes for the electromagnetic radiation, will give you a measure of the range, because the electromagnetic radiation is traveling at just about the speed of light. And so the time difference will tell you how far things are. And here's the equation. If this is the round-trip time the round-trip time, it's twice the range to the target over the speed of light. Okay. Now, as I said, trust me, it's going to get more complicated, and that's why I gave you a preface up front. This is a very quick overview. Now let's talk about the early days of radar, how it all came about. Radar experiments were being done, and the principles of radar in many different places. And different people contributed in different experimental groups in the 1920s and 30s, got to understand that that when they were using their communication systems and an aircraft would get in the way of the communication system, they would notice a scattering, an attenuation, a disturbance of the received signal by the target. And then they got the idea, hey, some of the energy comes back, and I could understand the distance away of that target. And scientists, I believe it was at the Naval Research Lab in the United States, could tell when ships were passing by a communication site on two different sides of the Potomac River, I believe it was, that the ship was passing by from the change in the signal. Many consider Sir Robert Watson Watt in Great Britain as the inventor of radar. He actually was granted a patent in 1935, but the significant work was done in many other countries. And Britain, because they were so close to the Nazi threat of Germany, that they worked hard to develop radar into an operational system. And they were way ahead of anything that was going on in the United States in the late 1930s. And he led the development of the first radar air defense sensor system. And it was called the Chain Home System. And it had an adjunct to it, Chain Home Low, went after low targets. We'll see about this in a minute or two. And a host of other radars that were developed by Great Britain at the very beginnings of the war, and were under development there. But in the 1939, early 1940, Great Britain and the United States realized that Great Britain could indeed be overrun, and so they sent over a mission with one of their scientists, Sir Tizard, and he brought over with, I think it was 7 of their experts, this famous box full of equipment. We'll talk about that in a minute. That contained some of their recent inventions that were revolutionary to radar. And that use was magnified. Here's a picture of Sir Robert Watson Watt. Now, I mentioned the Tizad mission to the United States of their scientific and technical people. Yes, it was 7 radar experts and a black box. Now, in that black box was everything they knew about radar and an incredibly interesting device called a cavity magnetron. It was a way of generating electromagnetic energy at short wavelengths, 10 centimeters, about that much. Up till that point, the chain home system was using magnitudes more wavelength, and that made the antennas much, much larger. The practical antennas were much, much larger, and, for instance, couldn't be fit on airplanes. And so possession of this cavity magnetron technology turned out to be critical in helping jumpstart the American war effort. And when this stuff came over, now this is a photograph courtesy of a colleague of mine, Eli Bruckner, that he took when he was over in Britain. This is the original 10 kilowatt pulsed magnetron for 10 centimeter wavelength. It's the original one. I believe he took that photograph in a museum. And then the United States realized the importance of what was going to happen, and they formed the radiation laboratory at MIT, where a huge amount, we're going to talk about that in a little bit, a huge amount of radar research and development was fielded. Now, the radiation lab operated between 1940 and 1945, and it was one of those tremendous efforts that a country puts on in wartime. We all have heard of the Manhattan Project, where the atomic bomb was developed, and it turns out, well, if the country's university professors realized you were really, really smart in science, physics, and engineering, or chemistry, or the field needed, you either went to Los Alamos and were working on the atomic bomb, or you went to the radiation lab, or also to Johns Hopkins Applied Physics Lab, where some fantastic work was done in proximity fuses, which we'll get to in a minute also. At the radiation lab during the war, many, many radar systems were developed and fielded for the first time for war use. This was serious business. The world was at war. And they exploited that 10 centimeter wavelength cavity magnetron invention. I'm going to show a system that does that. And the laboratory grew. And just imagine, the whole length of the Rad Lab, as it's called, was the order of 5 or 6 years. It grew to 4,000 people. And to give you an idea of how bright these people were, 9 of them went on to receive Nobel Prizes, most in physics, some in other fields. And a lot of the original people in the Rad Lab were physicists, an awful lot of engineers. And they designed almost half the radars in World War II, more than 100 different radar systems worth $1.5 billion. They'd build the first one, test it out, and then it would go out to a newly created company who would build hundreds of them for the field. And this is the home of the MIT Radiation Lab. When I was an undergraduate at MIT, this was the Sacred Building 20 many of us did research in, and the home of many great, after the war, many great technology developments at MIT. Now it has been taken down, and a multi-story modern building for all kinds of new and great research has taken its place. And here's a photograph of one of the, I would say, one of the most prominent radar systems that was developed during World War II. It was called the SCR 584. We're going to talk about that in detail. And that is indeed a 10 centimeter magnetron radar. I might add that radar development had been going on starting in 1940, and much to the chagrin of people afterwards, one of those radars, an SCR 270, I believe it was located on Oahu on Opana Point, north of Pearl Harbor, which was in the south, and it detected 55 minutes before the attack on Pearl Harbor, it detected that fleet of aircraft coming to attack Pearl Harbor. The operators of the radar recognized it as what they call a blip on the screen. No digital CRTs like we have today in our computer systems. It was just a little bump and a CRT. But they recognized it as a huge signal that was traveling at the airspeed you'd expect aircraft to come, and it was coming from the northeast. And that was the direction. They immediately sent forward the information to a control center, which was unfortunately an inexperienced lieutenant was at the center. It was, we all remember, a Sunday morning, and he just said, it's that fleet of B-117s, bombers coming from the West Coast that we expect sometime this morning. And indeed, it wasn't. I read the congressional testimony in the hearings afterwards, and it was one of those things where human beings make a mistake, and we actually would have had a 55-minute warning of the attack if that radar detection had been taken seriously, sent down the chain of command, and general quarters were taken. There would have been obviously serious damage to the Battleship Row, but how it would have changed it we'll just never know. But the attack was detected ahead of time, and obviously in the aftermath of Pearl Harbor, radar was taken very seriously, very quickly. Now we're going to look in detail at two examples during World War II of the impact of radar on World War II. And the first one I used in an earlier video. The second one is a new one, and I'm just going to mention briefly some other examples where radar, just say the words in a sentence or two. The first one was in the air defense of Great Britain during the Battle of Britain in the summer of 1940. I want to set the stage for you. World War II has not yet started. France has fallen. Dunkirk has happened. The Lend-Lease program has started, and we are pouring what supplies we can into Great Britain. Britain's army was defeated, along with the French, and the orders of 100,000s of troops came back. Many were captured. Things weren't good on the British Isles. They were very concerned about invasion. And the obvious point, which the Germans were planning to come across and building up a fleet of barges, was at Dover, where from the cliffs of Dover you can look over and 12 miles away you can see France. And we're right now, we have the tunnel that goes from Great Britain to France, and you can go under the tunnel. They were very close. And what the Germans had to do was achieve air superiority over Great Britain. The reason they had to achieve air superiority was if they didn't have a great fleet of battleships and cruisers anywhere near the great fleet that Britain had, which they kept in harbors up in Scotland and relatively free from air attack. They weren't that vulnerable. They were relatively safe. But if a landing was started, which would take a day or two or whatever, there was plenty of time for this fleet to come down and sink the invasion fleet. And if Germany had air superiority, it knew it could sink the fleet when it came out into open waters. There had been many instances where the Japanese had sunk British capital ships in the Pacific. People knew that airplanes could sink capital ships quite readily. So the Germans had to get air superiority. And also, they were bombing Britain, and they wanted to bomb it into submission. And so what the British did was set up a system of radars. Initially, there were 21 early warning radars, and I'm going to explain what they were and how they worked. The remnants of these radars, their transmitting towers, still exist over in Great Britain. Many of them are used as cell towers. They were made of steel. They're several hundred feet high, and they came in triplets. And as you see, I explain the antenna system, you'll understand. This photograph is courtesy of Bob Cromwell, who took it in September of '06 on a trip over to Dover. And it was the antennas, which I'll show you, are hung between the towers in a moment. This was the site at Dover. And this was their line of air defense, so that they could tell if they were being attacked. Well, why was this important? I'll tell you it right up front. The Germans had about 1,500 fighters and pilots. The British had about 1,500 fighters and pilots. And they would come in from captured France or from some direction. They'd come in a vector, carefully concentrated, to go in and out quickly. Remember, this distance is just 12 miles, 15 miles. It's a very small distance, and the planes typically will go 250 miles an hour. So they could go in, drop their bombs, London's right here, and get back home without Britain being able to focus in that one place their fighters to knock down the bombers and to fight the fighters and do battle. Because they were too thinly spread with all their scattered airfields. They had to be scattered, or if they were in one lump place, they could be attacked and destroyed on the ground. Now let's look at the air defense radars that the British built. These used the technology of the day, very long wavelengths, 10 to 15 meters, and frequencies between 20 and 30 megahertz. So 30 feet to 45 feet was a wavelength. And dipole antennas can be built at a half wavelength. And there's a string of 8 dipole antennas. We'll look at this is the transmit antenna, and another string of the very dark lines of the active elements strung between the towers. And the antennas were built in duplicate for backup. And then these were made of steel, and then a set of wooden towers that held crossed dipoles, high and low, which were used to receive the backscattered signal. The beam width of the pattern of this was about 100 degrees. You say, gee, 100 degrees, how can you tell where anything is? We'll get to that in a minute. They operated at a peak power of 350 kilowatts, developing all the peak power they possibly can. The point is, they could detect at approximately, at high altitude, that'd be like 20,000 feet for them, at 160 nautical miles, a Junkers 88 German bomber. So they could see the bombers coming if they were coming high at 160 nautical miles. This artistic visualization was developed by an artist, Chet Beals, in MIT Lincoln Laboratories Graphic Arts Department, and he developed it from a British paper which described technically what the system looks like. And I could not find anywhere a really good visualization of what the chain home radar looked like. And from that technical paper, which has very crude drawings, not at all to this beauty, this drawing, and with permission of MIT Lincoln Laboratory, we're allowed to use it. And a British radar expert, has told me that this is probably the best visualization of the chain home radar system that he's ever seen. Now here's a picture, what I call a technical picture of the radar. The elements were, you see these dark elements were half a wavelength long. To get more gain, directivity in the vertical direction, there was a row of them, 8 of them, a half a wavelength apart, and then a gap filler antenna to make a beam at a lower angle. And they were up at the tower was steel and 360 feet tall. And then one of the received towers, here's just one of them we've visualized here, they were wooden and 240 feet tall. And what they would do is they would receive the signal with a cross dipole at 95 feet and 240 feet, and look at the phase difference of the signal in altitude with one set of receive antennas. And they had, of course, 4 of them, as you remember. I'll go back just for a moment. They had them side by side, and they'd look at the differences of the signals from the side-by-side reception and the up and down reception combined to look at that phase difference to tell where within the 100 degrees the flight was. So they could, so to say, split the beam down from 100 degrees to the order of 5 degrees. So they could do 5 miles or so. And they could tell to about a 5 mile by a mile or 2 or 3 section where the attack was coming from. And that was fantastic to know. And let's look at a visualization that will tell us first what these pictures looked like. These photographs became in the public domain, I think it's somewhere in the 40 to 50 years after they were made. These photographs that are black and white are courtesy of the United Kingdom government. They were all taken by British military people, and all photographs taken by British military personnel after 40-something years become in the public domain. So it's now we're able to see them. And here is a female operator looking at a oscilloscope, looking for those blips of where there was a received signal, measuring the range with templates. And here is a device called a goniometer. And by twisting that goniometer so that there was a balance between the upper level of receive and the lower level, and the right and the left, one could do the beam splitting. And here's a picture blown up a little higher of the receive huts. They were located mostly below ground and battle hardened. And then they would take that information. And by the way, up here is a picture from a museum in Great Britain of the chain home transmitter itself. And here is a plot room where the receiver operators would plot the position and range, would send the position and range and azimuth to a station, which would be the command and control center for the site, and then to an air operations group where they'd have little markers on a giant map of the lower section of Great Britain showing the progress of the attack, and then via telephone lines alerting the British fighters where to go to meet the attack. So that, this is terribly important, so that I'll get to that in a minute, so that they could focus their attack and have even parity with their fighters and the British fighters, and we'll get to the results in a minute. One of the things we'll go over in propagation is when you have very long wavelengths like this, like the chain home, there are at lower elevation angles gaps in the coverage. And the British built a higher frequency at 200 megahertz as opposed to 20 to 30 megahertz system of radars with the new technology that was being developed to fill in low elevation coverage at less than 2 degree elevation. And they could detect at an aircraft coming in at 500 feet at a range of 25 miles. So they were continually, during the process of this, from the summer of 40 to September of 1940 was the real crux, hard part of the Battle of Great Britain. They were continually upgrading that radar system to fill in the gaps in the coverage and add lots of new radars at frequencies that got up into the S-band region and had ground control intercept radars, etc., which you'll learn about. So it was a continual system of making the air defense system more modern. Now here's a map. I showed you earlier the same map of Great Britain with 20 radars, and here's what its coverage would look like with about 160 miles of coverage. And you could see that it turns out there's plenty of time to see them coming. And I go over here the logical progression that I went through with you. The radar was what I call a force multiplier. With airfields scattered all over the place, they were able to use radar to concentrate their defenses right at the location of the German attack and focus their limited number of interceptor aircraft so that they could achieve numerical parity with the attacking German aircraft. The effect on the war was that Germany was not able to achieve air superiority, and the invasion of Great Britain was postponed indefinitely because they could not. Now, that allowed, over the next 4 years, Great Britain to be that island of democracy where huge amounts of material from the factories, the war factories in the United States, and men, millions, could come and use as a staging area for the attack on Europe. If that attack had to come directly from the United States, it would have been far more difficult, far more difficult a job, and it just made a big difference in the war, you can see. And now what I'm going to do is take a quick break and then go to the second example of radar in World War II. Now we'll start the second part of the introduction, lecture 1, and let's move on. Now we're going to look at the second example from World War II of how radar made a big difference. And it has to do with the first cruise missiles that were ever developed in the world, called the V-1, or buzz bombs. Here's a picture of the buzz bomb. Let's look at what the threat was from this. It was an unmanned cruise missile. Its propulsion system was a ramjet located here in the back. It was guided by a gyro compass autopilot. It could go had a range of 250 kilometers, and it had about a ton of high explosive warhead. And the Germans launched about 9,000 of these in the 40s, in the mid to the late 40s. Excuse me, I was thinking the mid to late part of the war. The latter part of World War II, and about 2,400 of them impacted the London area. A great number of them were shot down. Initially, of course, they fly at about 400 miles an hour, which is pretty fast, but they fly a very straight line at a relatively low altitude of 2,000 to 3,000 feet. And the question was, how do you knock these things down regularly and easily when they're pretty fast? And it's hard. And there were difficulties in that. And I want to point out how radar got the kill rate up to just about 1, very close to 1. And there's a set of radar technologies that were involved in that. The first of these was the radar I talked a little bit earlier about, called the SCR-584. It has a 10 centimeter wavelength, that's a couple of inches like that, and about 4 inches, 3,000 megahertz. It had a magnetron for power, which generated 250 kilowatts of peak power, and a pulse. It would send a pulse out that was a little less than a microsecond in length, and it would send out a burst of pulses a little less than 2,000 in a second. This antenna is a little less than 6 feet in diameter, and it had a 4-degree beam width. And its azimuth coverage was 360 degrees because this antenna could rotate in azimuth and in elevation. It had a maximum detection range on an aircraft of about 40 miles and a range accuracy of 75 feet and a remarkable angular accuracy of 6/100ths of a degree. Okay, so it's a very accurate radar system in terms of being able to see 360 degrees, and then when the operator saw a target of interest, to lock onto that aircraft and follow it very, very, very carefully. Okay? Now, here's a picture 40 years after the radiation laboratory, at its anniversary, of the SCR-584 with a couple of the gentlemen. Notice the white beards, and the white beard from Leo Sullivan and the white hair. Leo was in his 20s. He was a young guy. He was like the young guy. And Leo got sent to the war to test it and to help get it operating. And I'll get into that story. He has a wonderful oral biography that is one can access on the IEEE website. If you just said Leo Sullivan, IEEE, and you Googled that, and you said SCR-584, you would get Leo's 40 or 50 page oral autobiography biography that you could access and read of his remnants. Leo has since passed away about 5-6 years ago, and he was just a fine gentleman. He was a group leader at Lincoln Laboratory when I was in my late 20s, and so I got to know Leo, just a great guy. But the heroics that what those guys did over in World War II, in the air defense, I'll get into in a minute. And anyway, you can see the parameters of this radar. It's the same as were on the previous view graph, but they got, for the 40th anniversary, they actually got this radar up and running from the museum, and they actually were tracking aircraft with it. 40 years later, the guys went back to the console, you know, forget these things after a while. And the excerpts from the reunion of the, Leo wasn't the only person, there were about 7 or 8 people who worked in the development, who were at this was taken at Millstone Hill in Westford, Massachusetts, a research facility of MIT's Lincoln Laboratory, and again, courtesy of the laboratory for this photograph, for its use. They all had a grand time, and it was movies, videos, all their remembrances were incorporated in a public broadcasting system, NOVA. And I think it was something like the invention that changed the world, or how radar helped World War II, or whatever. And it was many years old. You can probably get it from your library if you do a search. You can get it's certainly not on a DVD. You can get it on a VCR. It's a really interesting tape where the guys talk about some of their exploits. But okay, now we move on to the second triad of the 3 instruments that were part of the air defense system that knocked the daylights out of the V-1. The second was the radar proximity fuse. Here we have a photograph, courtesy of yours truly, and here is an actual 1980s version of a radar proximity fuse. And there's a dielectric warhead that holds the antenna, and they operate at around 200 megahertz. They use Doppler frequency shift of the radar signal that's emitted out to detect the moving target, and when a threshold is crossed, the fuse is detonated, and that allows physical destruction without hitting the target. And that is a crucial thing. You don't have to be able to have this when it's hooked on to an explosive charge, be it an anti-aircraft missile or an artillery shell, to explode it and knock down the aircraft, or the V-1 in this case. But you can just get close enough for the kill. And in many cases, 5, 10, 15 feet would be plenty and then you'd get close enough and you'd knock it out. Here's a cross-section that I got from the web of an artillery shell, a proximity fuse of about the mid-1940s. And they all look, it turns out, there's miniaturization, but the point is they have to operate under very, very high acceleration as the anti-aircraft shell or an artillery shell is shot out of the barrel, enormous accelerations, and they have to have a radar that will work that well. And during World War II, Johns Hopkins Applied Physics Laboratory just broke the ground, and they made this kind of the V53 proximity fuse work like a charm. So when it got close to the V1, it would wipe it out. get, the shards from the shell would destroy the V1. So you've got a weapon that can kill it. You've got a sensor that can find it and track it. And what else do you need? Well, you need this device in the middle. And here's a block diagram of the whole system. This was developed by Bell Labs, and it's actually an analog computer. It would take the data from the SCR-584 of where the target was at a given moment in time, project ahead where it would be if at a slight time later an anti-aircraft gun, either the US's 90 millimeter or the British's 3.7 inch anti-aircraft gun, fired, and it takes time for that shell to reach that predicted point of the aircraft as it moved while the shell was going up towards it, and it would send direction information to the anti-aircraft guns to tell them exactly where to point and to fire, so that when the shell, there'd be an intersection of the shell and the aircraft. And when the SCR-584s were first sent, and obviously very quickly to Great Britain, they were set up all on the coast of Great Britain, the lower coast, where they wanted to get those V1s before they could get to London and do devastation on the civilian population. They were indeed a weapon of mass terror. And the British had a kill rate without the radar, and with the British aircraft knocking them down, that was reasonable, but it wasn't as good as you could make it. And when Leo Sullivan arrived, and they realized that the operators, who were just getting used to it, didn't understand the manuals. So in his autobiography, Leo says, they got a hold of a Red Cross ambulance, blacked out the white cross on the ambulance, filled it full of manuals on the SCR-584, and went from radar battery to radar battery, or I should say air defense system. They locally isolated for their area of coverage, teaching the operators how to operate the system, operate all three components as a system. And immediately after a very short time, they get the guys up and operating, and boom, they were just getting them right and left. So they went one after the other, working day and night, till they got everyone all tuned up and running, and they got the rate up very close to 100%, very close to 100% by the end. By the time the V1 launching sites were overrun by the troops that had invaded in Normandy. It was like the stats are in Leo's book. It's like a 97 out of 104 over a certain period. They got so it really made a difference in that air defense system. Also, at the same time, roughly, another one of the operators from the Rad Lab, another young guy, went over to the Anzio beachhead in Italy, where the Germans operated the high ground. They had a lot of artillery, but they're also bombing the troops on the beachhead, which they couldn't get off of, every night. And he rushed over. They were using a radar system. I think it was the SCR-268, which the Germans knew how to jam. They knew what frequency it was on, and they could jam it and make it inoperative. So they brought the SCR-584s over. They dug them into the ground so that only the antenna was above ground. And the first night, and these operators finally knew how to operate the system, and they hooked it up with 90 millimeter AAA and the M9. And the Germans had been sending over, a dozen or more bombers each night when it wasn't easy to shoot them down. And the first night, they sent over 12 bombers. And the system knocked down 7 of the 12. Well, no pilots are going to fly when they lose that kind of aircraft. So a week later, they sent one more bomber over at night. It got knocked down, and they just didn't send any more bombers over. It's that kind of efficacy that this system had. And really, it's a neat, tells you. Now I'd like to go over the radar basics. What are the positive and negative aspects of radar, what attributes it measures, and the block diagram of the radar system. We'll move on. Okay. The good things about radar is it's about the only sensor that can look way out and give you good long-range detection of targets and track them at thousands of miles. Today's radars. They can see very far and see over wide solid angle, very wide. And they'll operate pretty much in all weather and day and night. And you got to look pretty hard to find something else that comes even close in sensor technology. They've got the wide area surveillance capability. And since we're dealing with transmitter systems today that are coherent in operation, and that is from group of pulses to group of pulses, they're coherent. You don't lose the phase information. It doesn't become scrambled between one group of pulses and another group of pulses. We can use that property, and we'll go into it in great technical detail later on in several lectures. We can simultaneously detect targets really well, and we can reject unwanted targets that you see, what we call clutter. Unwanted backscatter from the ground, unwanted backscatter from rain, from things like chaff, aluminum that's dropped from airplanes. That was developed during World War II as a way to confuse radars. From the sea, birds, when they're in close, appear to be big targets, and I'll explain why later. Or if your target is very small and the birds are very small, you've got problems. But anyway, because of this coherence, you can also image targets, both fixed and moving. Fixed with so-called synthetic aperture radar techniques, and moving targets using the Doppler principle, which I'll explain in a couple of view graphs. And we're going to show you that this coherence allows us to take a line of sources of electromagnetic energy and phase that energy such that you can point the beam electronically by changing the phase of the different transmitters along a line. If you can change that phase very fast, you can point the beam over here and then microseconds later point the beam in another direction. You don't have to move a big antenna, some of which I'm going to show you are hundreds of feet in diameter. So you don't have that mechanical inertia to point the antenna in different directions. You can electronically scan the beam in microseconds. And you also have the ability to adaptively change the shape of the beam so that you can mitigate interference and people jamming the radars with unwanted extraneous noise. And the other great thing about radar relative to other media is that it's relatively lossless, and you've got relatively straight line propagation at microwave frequencies. And you'll see when we talk about propagation and what we mean by relatively. There are some media that are just hard to work with, like sonar. And actually, this relatively refers to a microwave at frequencies down in the 10 to 30 megahertz region. When you send a beam up, it hits the ionosphere and bounces back, and the losses you get in the ionosphere can be huge. But at microwave frequencies, you've got these good things. There's no free lunch in the world. That when you come with those positives, you're going to get that long-range detection, very far range. You need big antennas, big structural objects that are heavy, and you want a lot of power. Antenna size and power will give you that range. We'll see later when we discuss things quantitatively. And we use a lot of electrical power to generate the microwave power. And these big radars that really see out thousands of miles cost a lot of money. And some radars don't. Police radars, $1,000 or something. A radar you put on your sailboat or your power cruisers, a few $1,000s. But if you're going to want to see aircraft long distances away, you got to pay some bucks to do it. You know, that's like a 5-star restaurant. If you really want to reach out, you've got to pay the bucks. You don't get a McDonald's price for a prime rib, you know. And the radar beams do not propagate well through the earth. You can't see into the earth, into water, and it's hard to get them to go into foliage. At frequencies the order of 100 megahertz, they'll go down into the canopy of trees. And they don't see around corners, you know, around obstacles like through a building. You can't see through buildings easy. You know, a steel, you can't see through a building, you know, through a mountain. They're vulnerable to jamming and anti-radiation missiles. You're emitting radiation. Someone can put some antennas up and say, aha, where the signal's big, that's where the radar is, and you can home in with an anti-radiation missile. And the target can detect that's being illuminated. So if something, you can see it, it can know where you are. And it can locate the target in angle-angle space. Excuse me, you can locate the radar in angle-angle space by listening and having a couple of antennas set up. Now the echo from some targets can get very small. Anyone who reads the newspapers can just Google stealth, low observable technology, B2, F-117, and you can read about that, and that's a difficulty for radars. And but of course, because of the sensitivity, we won't be getting into that. Here are some pictures of different radars highlighting what they're used for. Here are some surveillance and fire control radars. Obviously, the word surveillance says it looks over a big amount of space, and it can tell me anywhere in that giant amount of space, solid angle, angular space, and range where things are. And it also can do fire control. That is, it can direct fighters or missiles to where the object is. That SCR-584 was both a surveillance and a fire control radar. And these radars are big, hundreds of feet. These are electronically scanned phased arrays. This is an electronically scanned phased array that's used to track and surveillance and for missiles. Inside of this big radome out on the island of Kwajalein is another system protecting the fleet on 4 sides of the destroyers and cruisers that protect each battle group are phased array radars. This is the Arleigh Burke class of destroyer, and here are 2 of its phased array radars. Each one looks at plus or minus 45 degrees, so 4 of them cover all 360 degrees. And here is a ship-based antenna that is used on a lot of destroyers and on some aircraft carriers to detect aircraft that are up in this nearby the fleet. Now we move on to airborne radars. You've always got the Earth is curved. You know, we learned that, and since it's curved, you can't see out forever. You got to get up high to see far away. And if you're on a ship, you've got a certain horizon. We'll get into the equations of how you figure out what your horizon is. And so for an aircraft carrier and its battle group, it wants to have some radar eyes above the fleet so it can see out a couple of 100 miles at least, and so it uses this E2C. This is a rotating antenna on that E2C that goes above the fleet and looks around and sees things that you couldn't see with a radar on the ship. You've all heard of the AWACS radar probably. This is a picture of the antenna which is inside that radome, and it has a 10 centimeter wavelength. And here is another this is if you look inside of this, it looks like an a command and control center, but really underneath the command and control center is where the transmitter is, and here's the antenna. Receive is there too, but it does surveillance, fire control, and command and control high up for the Air Force. And also for ground surveillance, the Air Force has the Joint STARS system, which was used in the Gulf Wars, both of them. And it has in this radome underneath this antenna. Here's a picture of the antenna when it's on the ground and the radome's opened up. An X-band radar that can see pictures on the, it can tell you the battlefield in a significant area. And a couple of the pictures have been released, just two that I could find in the public media or on the web and the public domain. And also we have in fighter aircraft, when they want to knock down other fighter aircraft or bombers, they want to look out far away and fire missiles at the aircraft that are out there, bring them and see what's there, see where the enemy is, and go after them. And airborne radars are located, let me go back, in the nose. And this is a planar array on this jet aircraft. And here is a more complex phased array inside the nose of another jet aircraft that can do not only, this has got a multi-mission mode, not only do surveillance and tracking, fire control, but it can also look on the ground and do things such as synthetic aperture radar, map the ground, and look at moving targets on the ground that it can do battle with. And in unmanned air vehicles, like Global Hawk here, radars are placed to give battlefield awareness to unmanned aircraft so that they can see where the bad guys are and take care of them. Now, radars aren't only used on those tactical missions, but a great many radars, huge ones, are used, so-called instrumentation radars. They're like the referees, the scorekeepers. If you want to test out something, action that's going on in the sky, like a missile defense test, or you want to fire, have a fighter aircraft fire a air-to-air missile at a drone and see how well it performs. You want to use a radar like this multiple object tracking radar that the Army has built, that Lockheed Martin built for the Army, and it's used at a lot of test ranges. Here are a bunch of radars at these four that are located out on the Kwajalein Atoll in the Pacific that are used as scorekeepers and data gatherers for missile defense tests. They give you an idea how the frequency range they operate over. This operates UHF and VHF frequencies. That's from 400 megahertz to from say 0.4 meters to 2 meters on two different frequencies it operates. And then this radar, the radar inside this radome, has a wavelength of a millimeter, 35 and 95 gigahertz at two frequencies. It's a dual band. This radar inside this radome operates at 5 centimeters, and this is TradeX, but it operates at a S-band and L-band, 10 centimeters and 23 centimeters. This guy here is so big that I think it's 120 feet across, and when it rotates in azimuth, there's a set of railroad tracks down here. Okay, and I'll show you later the picture of a human being, a man, who's up on a little galley next to this antenna. I'll give you an idea of the size of it in the antenna lecture. These are big instrumentation radars. Okay, radars are also used extensively in the civilian world. Here are two photographs of the mainstays of our air traffic control system, the so-called airport surveillance radars. This is an ASR-9. I believe this is located, one located in Boston, and also the ARSR-4. These were built, this one was built by Northrop Grumman. This one also was built by Northrop Grumman, although the picture is courtesy of Lincoln Lab. Here's a real serious-looking military policeman with a speed radar measuring speed. And also on top of air traffic control towers, you might have noticed a pancake-shaped radome. This is an ARSR-4. An ASD-4, Airport Surface Detection Radar Model 4. And The ASD-4 looks at targets that are moving slowly near the surface of an airport. So you can see that aircraft on the runways aren't going to collide one with another. And then the Weather Service, NOAA, and the FAA operate a series of radars that are used for different important functions. There's the Terminal Doppler Weather Radar that looks near its position at a significant number of airports where there's a lot of turbulence. And microbursts can occur that have caused deadly accidents, tragic accidents, where planes coming and taking off have crashed into the ground from a sudden change in the vertical wind velocity. And this radar is used to detect those microbursts, automatically tell the air traffic controllers and vector pilots away from landing or taking off from those runways when those events occur. And then also the NOAA has a huge, vast complex of weather detection radars. Goes by two acronyms, WSR-88 and NEXTRAD. And those radars, and we'll see pictures of them, the data from them, they're used to measure weather fronts and dangerous weather fronts that are coming, and give your weather. If you're looking a lot of the time at your local weather forecaster, these radars. So there's a lot of civilian uses, and even more. NASA uses them to track its missiles and space missions when they're taking off. NASA built this ground penetration radar to understand what's below the surface of the ground, use it on a extraterrestrial body or whatever. And here is a ground penetration radar. Archaeologists use these a lot to look for where interesting sites might be. And you can see an operator here and a person moving the ground penetration radar to see. They don't see very deep, but they see deep enough that you could see a buried body or artifacts for an archaeological dig. Radar was used by the Magellan spacecraft to map Venus. The synthetic aperture radar was built out at Jet Propulsion Laboratory. And lastly, you can't go by a civilian dock where there are lots of powerboats and sailboats, and you don't see radars that detect the buoys that are located coming and going out of harbors, so that mariners in fog and at night can tell where they are safely, along with GPS is now very helpful. Okay, so now what is it that radars measure? We're going to look at that next. Let's first look at what the pulse of a radar looks like, and the pulse set of pulses. And I want to develop some definitions for you. Radar, like every other technology, has its jargon, its acronyms, its sets of short words, or whatever it is, BFF, best friends forever, and you got to learn these things. They're the language of radar, and I want you to know what they mean. So we're going to go over them once quickly. The peak power is the peak power within a pulse, and I want to remind you that this is the envelope of power that is transmitted. Within this pulse width is a complex sine wave of electromagnetic energy, and it's oscillating up and down at some frequency. But the peak power is power versus time. The peak power is that biggest value it gets to, and the width is called the pulse width. And then sometime later you get an echo back, it's the target return, and a little while later you'll send out another pulse. And what we call the PRI, the pulse repetition interval, is the time between those two pulses. And usually there'll be a set of pulses. There could be just two, there could be 20, 32, 64, 1,000. Whatever it is, That's the PRI of that radar with that waveform. The duty cycle is a measure of, in an average sense, of what's the average that the average amount that you're turned on and you're turned off. So it's the pulse width divided by the pulse repetition interval is the duty cycle. And it says on average the transmit is turned on that fraction of the time. And that's the average power, would be the peak power times the duty cycle. And then the other quantity is the pulse repetition frequency, which is 1 over the pulse repetition interval. So for a radar that's continuously transmitting, its pulse length is just on and on and on, it's 100% duty cycle. It's always on. And just to give you an idea, not for every radar, and these vary over orders of magnitude, but what some numbers are, and these vary for what some radars are. Here are some numbers for, I picked, that's a reasonable one for a radar. You can have a peak power as much as a megawatt, more, less, often. Pulse lengths, just you could say plus or minus 1 or 2 orders of magnitude or something like that. 100 microseconds, you could have a microsecond. But the target return, I want to just point out, is very small. It can be as little as a microwatt of power. And so after you turn your transmitter on, you want to make sure that none of that transmitter leaks into your receiver while you have your receiver turned on. Important thing. And a kilohertz, a millisecond between pulses, is a number. Numbers go as high as 100 kilohertz, 10 kilohertz, 1 kilohertz, several hundred hertz. But those are the orders of magnitude of the pulse repetition of, actually I was giving you the pulse repetition frequencies. You could get, say, 1/100th of a second up to microseconds, fractions of a microsecond, which would correspond to pulse repetition intervals of, as I go through my mind, easily I can think of radars that operate at 500 or 600 hertz. And also radars that operate, and we'll see later why, that operate at 80 or 90,000 hertz. And the average power for this particular example is 100 kilowatts because we're running the transmitter at a duty cycle of 10%. Sometimes it's 0.1%, and sometimes it's 15-20%. It can go over those kinds of ranges. And that's just to give you an idea of the general orders of magnitude with big errors that these numbers can be. Now, what does a radar observe? What does a radar observe in terms of numbers? I went over some of this before. We obviously know we transmit out, and this is the signal underneath that square envelope of an ideal transmitted signal just for one pulse, and we get back. The transmitted signal goes out, reflects off the target, which I'm going to assume is going at a constant velocity v, and that's the velocity in the direction of the radar. Note that. It's not going across at another. I'll get into that issue a little later. But for this particular example, it's going in a direction v towards the radar. Everything's along a line. And there'll be a received signal, the echo off the target, we scatter back and go into the radar. The form of the transmitted signal is just this. It's an amplitude is a function of time, and that would contain the information saying there was no signal before this time. And then we got this exponential complex signal. This is obviously one of the real or imaginary component. And it's on for a while, and then contained in the A of t would be that it's 0 afterwards. And then what do we receive? Well, we don't receive the full signal back. It's attenuated. It's delayed in time because it takes time to go out and back. The delay time is tau, so you have to subtract that off. And then there's this other. The frequency of this signal we transmitted, has changed. And that is due to a principle called the Doppler effect. I'm going to note up here that the range to the radar of the target is just its range at t equals 0, and since it's coming this way, you have to subtract off the velocity times the time, because the target's moving. But I want to point out that the received signal's frequency is changed because of physical effect known as the Doppler effect. And I'm going to go over with you a derivation of the Doppler effect in a view graph or so. So we're going to be able to measure the amplitude of the target, which depends on the radar cross-section. We're going to have a whole lecture on that. Just take it my word. The parameters of the radar, how powerful it was, the range, how far away you were. We're going to have directionality from the antenna. The beam width of the antenna is going to be relatively narrow, hopefully, so that we'll be able to measure azimuth and elevation to certain accuracies. And we'll measure this time delay, which will implicitly give us, at a given time, the range that the radar is away. This is the, and then we have the Doppler frequency, which is twice the velocity, and that's the velocity along the line of sight of the radar, accurately. In this case, since it's all along the line, it's the velocity of the aircraft, times the frequency divided by the speed of light, which from electromagnetism, the frequency divided by the speed of light is the wavelength. So the Doppler shift is twice the velocity, the radio velocity divided by the wavelength of the radiation that you transmit. Okay. Now let's derive the Doppler shift, and again we'll derive it for a linear target, but it should be noted that the Doppler shift only depends on the radial component of velocity. Okay? Okay, this peak right here, I denote A, and one wavelength later I denote the peak B. And that peak A leaves at time t equals 0 when the radar is at R0. And the time it arrives at is a delta time later, a little bit later. And we have the aircraft moving with a radial velocity v. And if it were moving at say rising, the radial velocity would be less than the velocity along the line of sight of the target and the radar. But let's just assume that the radial velocity is along the line of sight of the full velocity vector of the target. The period of the transmitted pulse is obviously the time between the peaks, and the frequency of the radiation is 1 over that. So we have these relations which are straightforward. And we note that C times the change in is going to be the relationship between the distance of the target at this point, an arbitrary, after it's moved into delta t, will be C delta t, which is R0 minus the velocity times delta t, or that delta t is this R0, the total length divided by the speed of light plus that radial velocity. From this relation, one can see easily that the time when peak A arrives at is 2 R0 over that speed. The time when peak B arrives is 2, and a different distance because the target has moved a distance. So that distance is this different. It's not R0, but R0 minus Vt divided by the speed. Okay? Now let's move to the next. Now, the period of the transmitted signal is T, and the received signal period is just the time between the received peaks. And then we just looked at what the frequency was. This is the time it received peak A and B. And that difference in time, the period, is this. Its frequency is 1 over that, which leads us, with a little algebra, to the frequency of the received signal is f0 1 plus V over C divided by 1 minus V over C. Well, then we realized that the speed of light is 186,000 miles a second, 3 times 10 to the 8th meters per second. Very big number. To put this in perspective, the speed of light is much, 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 much larger than any velocity of a target we're going to deal with, like 100 miles an hour versus 186,000 miles a second. So we can approximate V as being very much smaller than C. And then this bottom denominator can be approximated by this power series. And when you do that, then the frequency that you receive is the carrier frequency that you transmitted plus 2V over C divided by the carrier frequency, which through simple manipulation of C over the carrier frequency is lambda. We get that the Doppler shift is plus 2V over lambda. And that was for an approaching target. For a target that was receding, we have a negative sign. And the gentleman who figured this all out was Christian Andreas Doppler. And here's a picture of the gentleman. So we see, here is the derivation of not the derivation, but the statement of the Doppler frequency, noting that this radial velocity, it's the radial velocity that counts. And this shift in frequency is positive for approaching targets and will be negative. There'll be a smaller frequency for receding targets. Okay, now I believe that is the end of this lecture, piece of this lecture. Well, now on to part 3 of the introduction in the Radar Systems Engineering course. Now we're in the middle of looking at radar basics, and now we're going to spend several minutes looking at a block diagram of a radar and giving you a big picture view of what a radar is and how it works. Okay, here's a block diagram of a radar system, and you can see that it's broken up into a number of key components. A transmitter section, and then there's a transmit-receive switch, and these blue lines show the path of the electromagnetic waves. And in transmit, let's just first look at the transmitter. The transmitter is generally made up of, you can imagine a large number of boxes, but these are the big picture block diagram functionality, pieces of functionality in the radar. And the first one is the waveform generator, where the waveform is generated. You know, the sinusoidal waveform, but at low, that's in the microwave region, but is of low amplitude. And then the signal is sent to a power amplifier, which will amplify the signal, give it the strength to go out and to detect a target that's very, very far away. These amplifiers can have gains of 4 or 5 orders of magnitude easily. Or you might run a series. This box would represent a series of amplifiers in series, a group of them in series, in parallel and in series, working together, so that the total gain output would be 10 to the 5th. Or it could be one large amplifier, one large tube amplifier. But in any case, there's usually a power amplifier subsystem. And then the energy goes to this switch, a switching mechanism. And sometimes it's a circulator, sometimes it's a duplexer, sometimes it's an actual a transmit-receive switch implemented in other ways. But its job is to isolate the powerful transmit signal from the receiver, which is going to, we'll see in a minute, is going to want to just listen to the very weak echoes coming back from the target. When we're transmitting, the signal will go out to the antenna and be given directionality by that antenna, which will be the medium which transfers the energy out to the medium where propagating out through, usually the atmosphere. Of course, it could be space if this was a radar on a spacecraft, until the electromagnetic wave, the microwave energy, hits the target, scatters off the target. The target will have a radar cross-section. We'll go into what that means. It'll have a characteristic which tells you how big it is to an electromagnetic wave, how much energy scatters back. And I just want to note that here we're going to be talking about the propagation medium too. Now, some of that energy will come back, and it will go back into the antenna. And the transmitter switch will, as soon as the transmitter stops transmitting, it will turn into the receive mode, where then the energy will come back and into the receiver section. The receiver will have an amplifier, it's very low noise, to amplify the signal, and then to convert it into digital format. Because these days with computers, all the processing of the signal, the separating of the target from background noise and from other targets, all that processing using the Doppler effect and other techniques will be done in the digital domain. And then the signal will go into the signal processing computer, where two functions called pulse compression and Doppler filtering, clutter rejection is the function, will be performed one after the other. And you notice as I talk about these things, I'm introducing a lot of words which I haven't very well defined. You're going to see that each one of the lectures following will discuss in detail these different subsystems of the radar. Now, after the signal has been compressed to give it high resolution, and we'll talk later about what that means, and we've used Doppler filtering in the frequency domain to reject unwanted, slowly moving targets moving at a velocity that aren't the same as the target. We'll go into a detection. We want to just note that the noise and the signal are random variables, and there's a probability associated with the signal having a certain voltage and the noise having a certain voltage. We'll have to go through thresholding. We'll talk about adaptive thresholding techniques. And then, after we've thresholded and we believe we've got a set of detections which are probably targets, we want to estimate the observables we talked about earlier in the lecture, the range, the azimuth, the Doppler, as best we possibly can. And we do that in the parameter estimation function. And then we'll go to track the object, and that is to correlate detections from one observation of that area of space with another, a different one, a sequential one after the other, so that we can track in time the location of the target as it moves in space, and also make the best estimate possible of where the object that we're tracking is, and then of course send the data to operators who will see on displays the location of the target and its characteristics. And these days we have very sophisticated digital displays, and also to record the data if that's an important function of the radar, so that analysts later can look very carefully offline at the data to understand how well the target was tracked, how well the radar worked, and to tune the radar in whatever means so that it's necessary, so that it's operating optimally. Okay, now let's look at one of the interesting characteristics about radars, and that is their wavelength and frequencies. If we look first of all at on a logarithmic scale, the wavelength and the frequency of electromagnetic radiation, we see down here that electromagnetic radiation extends over many, each one of these decades, each one of these little lines represents an order of magnitude. And so the wavelengths generally can go over from 100 meters down to 1/100th of an angstrom. So there's just a very large number of dynamic range to electromagnetic waves. And here we see where light is, visible light, infrared radiation, ultraviolet radiation, X-rays and gamma rays that are very small. And in here is the microwave region. And the microwave region is where most radars operate. Generally wavelengths from about a millimeter or so at its shortest, up to wavelengths as high as a meter or so, order of magnitude. But if you think about that for a minute, from a millimeter to 10 meters, from a millimeter to a meter, that's 3 orders of magnitude. And so you can imagine that the power generation techniques, the receiver techniques, the methods of transmitting energy along waveguides or coaxial cables is very different at these different, over 3 orders of magnitude. The technology involved is very different in making an amplifier in the millimeter wave technology than it is up at, although the block diagrams might look similar, the technology of implementation and is very different. And radars also operate, some radars do, so-called over-the-horizon radars, up to 10 to 30 meters. So we've got a potential here, 4 orders of magnitude, so that you're going to see that the technologies involved in building the radars and, among other things, how the electromagnetic energy interacts with the target, how it interacts with the atmosphere, will be very different over this very wide dynamic range. Now, if we just take the microwave band, which goes from about 1 gigahertz to 12 gigahertz, and I just put 12 here arbitrarily, the millimeter wave bands, you'll see that there are a number, 4 millimeter wave bands, where there are windows of relatively lower attenuation, which will allow transmission of electromagnetic radiation. There isn't a lot of absorption from water or oxygen, stuff like that. Those bands are up from the order of about 16 gigahertz up to 95 gigahertz. They're further up, but I'm just going to show you on a linear scale here from 1 to the order of 10 gigahertz, excuse me. And the space and frequency that is allocated by the International Telecommunications Union for radars are these different half a dozen bands. And they have a special nomenclature. X-band is in this region, and it's roughly about 9 gigahertz, 9 to 10 gigahertz. C-band is about 5.5 gigahertz with a corresponding wavelength of 5.5 centimeters. S-band, 10 centimeters at about 3 gigahertz. L-band, 23 centimeters, about 1.2 to 1.3 gigahertz. And then UHF and VHF, standing for ultra high frequency and very high frequency, at approximately, this is about 435 centimeters, and then 2 meters for VHF. And these are approximately. So you can see that when you look at them on a linear scale, they go from a couple of centimeters to a couple of meters, and then we've got the millimeter wave bands way up, and then you've got up the high frequency bands from say 3 meters up to 30 meters that handle over the horizon radar frequencies. So this points out that there's very, very wide dynamic range, not dynamic range, but a wide frequency extent and wavelength extent that radars operate over. Okay. And we're going to be looking at all the different properties at the different wavelengths and frequencies. Now, I deliberately put up here X-band, C-band, S-band, L-band, UHF, and VHF. And something, if you're going to go through the length of this course, you're going to learn sort of like a snap in your head. The same way pi is 3.14, 22/7, as you learned when you were learning algebra and geometry, I should say. You're going to learn X-band, you're going to think 3 centimeters, about 10 gigahertz. Same thing, S-band, 10 centimeters, 3 gigahertz. L-band, 23 centimeters, about 1.25 gigahertz, and likewise. Okay, now let's move on. Now for each of these frequencies, and by the way, these are the exact ranges that the IEEE has set as standard up that we should call these bands. The IEEE has a standards board, and standard 521-2002 all agreed that these frequencies from 3 to 30 megahertz was high frequency, from 30 to 300 megahertz was VHF, and on down. And I just wanted to point out that different areas of the frequency spectrum are used for different functions. And we'll see why that is later. In simple words, when you want to search, the important thing is power times aperture, the size of your antenna times the power that you have, that you're transmitting. And it's a lot cheaper to get aperture, to build a big antenna, than it is to put a lot of very expensive power amplifiers together, you'll see. And so if just what you want to do is to set up one big parabolic dish that will focus the energy in one beam, you're going to want a big antenna to do search. If you want, the antenna you're going to want to make as big as possible because it puts less stress on the power of the radar. And we see here 2 types of antennas. A parabolic dish that would track, have one beam, and a phased array radar, which will, this is one at this one is at UHF. This one transmits at both UHF and VHF simultaneously, and this is an early warning radar. It's in Filingsdale, England. Now you see that they are up at this region of long wavelength. Okay. Now if we look at tracking radars, they want very fine angular accuracy, and the angle is approximately lambda over d in radians, and d being the size of the aperture. And so you're going to want, to help you there, lambda for very small angles, you want the wavelength small. And usually tracking radars are in this regime. You have atmospheric attenuation issues that can give you more difficulty here than it's worth moving up to get some of the time. But here's the Haystack radar at Westford, Massachusetts, which is at X-band, and the inside it's I believe 120 foot radome, and huge radome. If you fly in from to Logan Airport, it looks like this giant golf ball on the ground. And this is a lens radar that's at C-band, a multiple object tracking radar built by Lockheed Martin, and it operates also at C-band. So you can see these are 2 typical radars, just to show you what they look like. This one is much bigger, has further range, and this one is used to look mostly at aircraft and near-in targets, the order of 100 miles or so. Now, next we look at radars where we want to have your cake and eat it too, I say. You want to be able to do both search and track, and they tend to be in the middle. They tend to operate between L-band, and some of them even at X-band, if you have certain reasons that you want to go to X-band to get a high bandwidth, among other things. And here are 3 different radars that a rotating rotating radar here, and we see a bunch of it's a rotating phased array, and it uses phased array elements and linear ones, and it rotates. And here we have the Aegis radar system. The Spy 1, here's its antenna, and it operates on destroyers and cruisers for the Navy, and it is the eyes of the fleet. It sees within line of sight out the order of well, I won't, hundreds of the order of magnitude of 100 miles at least. All aircraft flying in to protect the U.S. Navy fleet, and then the Patriot missile defense system, and mostly air defense system. It was used against Scuds during the first Gulf War, and it uses a C-band radar. I put these up just to show you that radars that perform functionally both search and track operate from L-band to C-band and even into X-band. Okay, now if we're going and we want to put a radar on a missile and use that radar as guidance to guide the missile to a target, we've got a very small aperture size for the missile, and so remember the angular size is lambda over d, d being the size of the antenna. We have to make the size of the antenna very small, and we're constrained to make the size, and so we're going to use frequencies that tend to be higher frequency. And here, so missile seekers would tend to be in this range. Now, if we're interested in, I call scorekeeping, that is having a set of radars which, when a test of a missile intercept, or you want to fly a missile and see how well it operated, and you want to measure the characteristics of that missile at many different frequencies. The radars that do this are called range instrumentation radars. And here we see the set of range instrumentation radars that are out at Kwajalein on the Marshall Islands that are used to measure the observables on targets, missiles that are flown from Vandenberg Air Force Base. ICBMs are tested, U.S. ICBMs are tested from Vandenberg into Kwajalein, and they cover the whole raft. The Altair radar back here is UHF and VHF. This is the TradeX radar, which is at S at L band. Alcor is at C band. Down in another part of the island is an X band radar, and this is the millimeter wave radar, which operates at 35 and 95 gigahertz frequency. So range instrumentation radars cover the whole gamut of frequencies. Now I'm just going to spend a few minutes talking about the different ways we classify radars. There's all kinds of ways that you can talk about. You can say, oh, it's a ship-based radar. It's and then you can talk about it by the platform, the waveform format, the waveform itself, and then there are these funny names, and I'll go over them in a little more detail, or the characteristics of the technology used or its functionality, the mission it has, and the actual function of the radar itself. And they can be a little bit confusing at times, but you'll learn in the course of this radar course what all these different things mean. When we discuss waveforms, by the end of it, you'll understand what all these different words mean: a pulse CW waveform, a phase-coded waveform. And when we talk about antennas, you'll learn the difference between a reflector and a hybrid scan, or a phased array, also called electronically scanned arrays. And we've talked a little bit about the frequencies, whether the transmit is solid state, does it do a functionality of its synthetic aperture radar, and then also the mission. Some civilian radars do air traffic control. They can also do air traffic control, of course, for the military, controlling air traffic around airports that military aircraft are. They can do air defense, ballistic missile defense. They can see into space. They can be airborne, giving the fleet early warning, or they can be airborne and looking at ground moving target, using moving target indication techniques we'll talk about. But then I want to focus mostly on There are names thought up by people. In this case, many of them either the company that built the radar, some people in the Pentagon or whatever, so you don't want someone to know their functionality, or the people, an acronym that could stand for a number of different things, like the PAWS actually here in this PAVE PAWS, which is a military designation. There are two-word military designations that can just be random words, but the PAWS was chosen for Phased Array Warning System. But anyway, the government also has a more rational system, and there's an ambiguity because some of these guys, everybody has this military number. And one thing you notice is the middle letter here is always a P. And I want to go over the code of this with you so you'll understand what this means. I'm going to do the code in a second, but I just want to point out that the PAVE PAWS radars, one of which is in Cape Cod and the other is out in the West Coast at Beale Air Force Station, they're called the FPS 115. The Cobra Dane radar up on Shemya is the FPS 108. The Patriot missile defense system, its phased array radar is the MPQ-53. Aegis is the SPY-1, and the Firefinder counter battery radar is the TPQ-37. So all of these radars have, if they're a military system, have a designation of this form. Now the question is, how is this designation? How does it come about? And this is how you break the code. You can actually look this up it's on the web, but before I think it appeared in Google, a lot of people would scratch their heads and say, what does it mean? And someone would hand them, years ago, a Xerox of what this meant. Now the first letter tells you what it's installed on. A is a piloted aircraft. F means it's fixed on the ground. And you can see I've highlighted in blue what radars would tended to be. You wouldn't have a W because you wouldn't, have a combined surface and undersurface system. But you can see that the first letter tells you what it's installed on. The second letter tells you what it is. And of course the P would stand for radar. And the third tells you something general about its purpose. G being fire control or searchlight directing. Q, special purpose accommodation. S meaning search, tracking, and Y, surveillance. So this is the code. This is how you break the code. And just show you quickly with one or two examples. Here we have a picture of the TPS-43, and they're typically followed by an A, N, / and then this code. So it's a transportable radar, so it gets a T. I've highlighted over here for each of the cases I'm going to show you the next 2 or 3 view graphs quickly. It's a radar, and it's used for detection and or search and or range and bearing and search. So that's what the TPS-43 does. It's a search radar. It tracks. And here's another, an FPS-16, which is an instrumentation radar used at many test ranges. And it's ground-based, it's a radar, and it also does search and track. We go to ship-based radar, the SPY-1. It's a surface ship-based radar doing surveillance and control, fire control and air control. Okay. And finally, the MPQ-64, it's also more popularly actually known, I think, to people as the Sentinel radar. I think probably the Sentinel came out of the program office, and then because every radar built by the military has to have one of these designations, it was the 64th MPQ that was built. And it's a special purpose or a combination of purposes. Sometimes people might put in the Q because they don't want you to know what it is. Hello again. Now it's time for the 4th section in the introduction to the first lecture of the Radar Systems Engineering course. This part of the introduction we'll go over an overview of each of the lectures in the course. There'll be one view graph, every now and then two, on each lecture topic. Now, the course is divided up into two sections, what I call the core section, which are the basics that everyone should know, and then other topics. And the core part is what everyone who's working in radar systems should understand. And then the other topics are more narrow, related to different applications of radar, and you'll see the juncture between them. First, we're going to go over, well, there's the prelude, which you've already seen, and then this is the introduction, and now into the meat of things. We're going to review electromagnetism and signals and systems and digital signal processing. And as I warned you before, I believe, this review is not going to teach you these subjects. Each of these different subjects could be the meat of a full one-term course. But it's to let you know the segments, the sections of electromagnetism that you should know and know well. And signals and systems and digital signal processing. Then we'll move on to the radar equation. Atmospheric propagation, detection of signals and noise, radar cross-section, which is effectively the size of the target scattering at a particular wavelength, how big the target is to the radar electronically. And antennas are a big subject. We're going to talk about the basics, and then talk about mechanical scanning in one lecture, and then electronic scanning and a hybrid of different techniques at the end of that lecture. Then we'll look at radar clutter, so-called its actual targets of physical objects in the world that give backscatter, but they're not the things that were of interest, like ground, sea, rain, things like that. We'll go over everything in more detail as we move along. Then we're going to discuss the different waveforms that we use in transmitting the microwave signals and methods that we use to so-called compress the pulse so that there's a lot of energy in the pulse, but you can still get a high resolution. And we'll go over those techniques in detail. Then we'll look at how do we reject the clutter while seeing the targets we want to see. And we'll go over the basic techniques. These all use the Doppler principle, which we will have gone over. And first, so-called moving target indicator techniques, which are a high-pass filter. So really, it passes through things that are moving and deletes things that aren't moving. Big thing that wouldn't be moving would be the ground. And then to more sophisticated techniques, pulse Doppler processing. These techniques were developed sort of in parallel as Moore's law allowed us to do inexpensively much more fast processing, because these require much more processing than the earlier mentioned techniques. That we'll discuss as an individual lecture, airborne pulse Doppler radar systems and the techniques used to deal with clutter from an airborne sensor, because remember what we said earlier about the Doppler effect. It measures the shift in frequency of the target relative to the radar. If the radar is on a moving platform, then all of the ground will be moving. So it's a much more complicated case to deal with. Then we're going to deal with radar observable estimation, target tracking, and then transmitters and receivers. Now, as I probably mentioned before, I'll reiterate again, these first 17 lectures, I've got all the view graphs done for, and they're well vetted. Then there'll be sort of a break as in the course as I develop the view graphs and the lecture itself for adaptive processing and synthetic aperture radar techniques. These are essentially mapping techniques using radars. Well, you can get up in a plane or in a satellite and use optical systems, but they can't see through clouds. synthetic aperture techniques allow you to see and map the ground without the problems due to clouds. And adaptive processing techniques are adaptive ways of both dealing with the Doppler rejection of clutter and also with dealing with putting nulls in your antenna patterns adaptively from interfering sources. So that's the outline of part one, the core of the course. And now what I call other lectures, techniques, and I'm not sure yet in which order I'm going to give them. I may, halfway, two-thirds of the way through the class, ask the audience to vote for which ones they'd like me to put together first or second. But these are the different topics, and I'll just, I'll be later on as part of this section that I'm videoing, I'm going to show you a view graph on each one of these, and we'll go over it in depth, and you'll see what that section will deal with. But the order of them, I'm not sure of what I'll have yet. And it would be really what you would find of the most use. The total length of each topic, each lecture, will vary from about 30 minutes, probably for some of these, to possibly 2 hours or even more. And I'm going to break up the video stream into segments. And the segments are what I call easily digestible segments, sort of like the tracks on a well put together audio book. I'm reading one particular audio book right now, and if it were all if one CD were the whole track, I wouldn't know what page to go back to. But this will allow you to go and have a nice juncture where you can stop and then go back. Easily digestible, not quite bite-sized, but I'll say snack-size pieces, and they'll vary in length, the order of 20 to 30 minutes in length, and I'll try to break them up into logical breaking points within the lecture itself. Okay. Okay, now let's move on to what each of the different lectures are going to be about. You're going to need to know about electromagnetism, and you got to have this at the tip of your fingers. And we'll go in the review in the next lecture. A review will be a review of electromagnetism in detail. And here's James Clerk Maxwell, which put all these different laws of electromagnetism together and to form a unified theory which works very well non-relativistically of electromagnetism. And in their differential form, which you should understand from your studies of vector calculus for the course, because you should understand what the divergence is, the gradient, the curl. You should understand those, the constitutive equations, which make up which relate the electric field to the vector, and the magnetic flux to the magnetic field intensity. And here's a picture of an electromagnetic plane wave going out in the z direction, where in the y direction we have an oscillating sinusoidal electric field, and perpendicular to it is the magnetic field. And those are just this is just a real part of the solutions to these Maxwell's equations for a plane wave with no sources in vacuum and non-conducting medium. And here's their equation form. Okay. Next, we're going to have a review of signal systems and digital signal processing. We're going to go over these things again very quickly. You're going to need to know about digital continuous systems, and here we have a simple sine wave, x sub t, the process that we all do nowadays, where we process the signals that in the real world are analog, and we digitize them with A to D converters into a discrete time system. And it's in the discrete time system that we do all of our digital signal processing now. And here's a discrete Fourier transform of this series, x of n being a number an integer, an increasing integer, 0 through whatever, times the time between sampling, and x of omega is the frequency response. And then we're going to understand both in the continuous and you should understand in the continuous and the discrete domain, continuous linear time invariant systems. And how if you put an input signal through one of them, you get y of t, and the system transfer function h of t, if you convolve the input signal with that, you get the output. And it's equivalent in the discrete time system, in the discrete time formalism. Other topics we're going to talk about are fast ways of doing a Fourier transform, called the fast Fourier transform algorithm, concept of convolution, sampling theorems. In other words, to figure out what exactly the frequency of this is, how quickly do you have to sample it? And if you don't sample it fast enough, a process called aliasing creeps in, which will cause the frequency domain to fold over on itself and confuse things. Need to understand that very well to understand Doppler processing. Then we're going to discuss digital filters, high pass, the concepts of high pass, low pass, and transversal filters, also called passband filters, and how we can weight these filters to reduce the side lobes of the filter, and the energy's got to go somewhere, so it'll make it a little bit wider, but will bring down the top, the gain of the filter, and the pluses and minuses of these, and how they're used in radars. Okay. Now next we're going to talk about the radar equation, and this is the glue that connects the characteristics of the radar, its gain, the directivity of the antenna, transmitted power, and the size of the target, and the range from the radar to the target. Also thrown in there will be there's factors about the propagation medium. So we transmit a pulse out, it reflects off the target of a certain size, and then you receive the pulse, and this connects them all. And what this ratio is, this is the power, the gain, the wavelength, the cross-section, a constant, or the cube of 4 pi, the range between the two systems, Boltzmann's constant, the system temperature. We'll go into these concepts, the noise bandwidth of the system, and the different losses from what I call the humanity of the radar. We'll get into all that in detail in the lecture. And this tells you the ratio of the signal to noise ratio, which you want to be high, so you'll have a high probability of detecting the target. Now, as we go through the atmosphere is not a vacuum, and the atmosphere can attenuate, reflect, and bend the beam through these different physical processes. We're going to go through these processes in great detail in a lecture all by itself. And then, once we've detected the target, and if we look at this as the received power in blue, and I've actually noted the noise in blue, and we have a reflection from a target here, and then another reflection from another target. If we apply a threshold to that received power, you'll see that, first of all, the noise goes up and down. It's a random process. It will have an average noise power, and the target will have an average power, peak power of its own. And here we see a case where if we apply this threshold, we correctly detect the target, we miss a real target, and we have as a detection, we think as a target, some noise that spiked. And we're going to go through the process of how we deal with the probability of detecting a target with a certain probability of false alarm. Now we'll look at the radar equation lecture in one view graph. We see here an antenna, and we see in detail blown up the beam of the antenna, and it's illuminating a target. And here we see that target blown up. Here we see the pulses coming in and hitting the target, and then the energy that's reflected back towards the radar. The way we characterize the electronic size of a target at a particular wavelength of electromagnetic radiation is it's the effective cross-sectional area of the target as seen by the radar. It's measured in meters squared or in dBSM, in decibel units. It's a power ratio. So that's that incident power density, watts per meter squared, times the cross-section equals the reflected power. And so if you know what the reflected power is, you know, and divide the incident power into the reflected power, you'll get the radar cross-section. And that can be measured as a function of aspect angle. And so that will characterize the reflective properties of the target. Okay, the next lecture will be on antennas. We'll look at the fundamentals of mechanical scanning techniques and mechanical scanning techniques. We're going to look at the concept of gain. What's the increase in directivity of the antenna over that of an isotropic source at its location. Here's a picture of a very large antenna located on the island of Kwajalein in the Marshall Islands, the Altair radar. And you can see that its sources are up here. And the gain of the antenna is 4 pi a over lambda squared. Go into this in a lot more detail. Antennas can also be steered, not mechanically like that previous antenna, Altair, but electronically. And this shows an example of a linear row of sources of electromagnetic energy, all coherent one with the other, and at this point here. But if we put in phase shifters, we can adjust the phase so that at a specific angle, scan angle, all of the maxima of the individual waves are in coherence, and they reinforce each other constructively. And so if you can shift the phase very fast, they're called phase shifters. First, they're made with ferrite, which you can change the phase fraction of a wavelength very fast. If you change those phases very fast, you can change the direction of the beam very fast, the order of microseconds or tens of microseconds. And here are two radar systems that use phase shifters. They're a big flat plate with thousands of phase shifting elements in them, lots of transmit-receive modules. Well, these particular ones don't have transmit-receive modules on them. The energy is transmitted out. This is a lens array, and the phase shifters are located in this face. And then the beam, the electric field from all the different phase shifters as it's transmitted to the different phases will come together, reinforce electronically, and have a beam in one direction. And here's the Aegis radar, which again is a phase shifted beam. Well, the whole concept of the whole study of antennas is big enough. It's going to take 2 long lectures to go over. Okay, now next to radar clutter. And this is, I've shown you a naval air defense scenario, and just to show you the different kinds of things with a picture that you can get back. Not just the echo from the target of interest, but receiver noise, atmospheric noise, interference from other targets that are jamming you, and just want to raise the threshold of noise in your receiver so you can't see anything out there. But backscatter from unwanted objects can be from the ground, from the sea, rain. Here we have the rain clouds, chaff, an airplane dropping chaff so that the dipoles all resonant at the frequency of your radar. Flights of birds can give you unwanted targets, and also show the ground. There can be ground traffic on nearby roads to the radar that can give you a problem. This is also just to remind you, if this were a radar on land and it's a weather service radar, it wants to be set up to see rain and not the ground. So one person's target can be another person's clutter. It's just a little addition to that. Now on to waveforms and pulse compression. The basic pulse waveform of a radar in a pulse CW mode is there'll be no transmission, and then the transmitter will turn on and transmit a sine wave of electromagnetic microwave energy and then turn it off. This is a pulsed CW waveform. And it has a certain time length, and the bandwidth of that transmitted signal is 1 over. The time of the signal is 1 over its bandwidth. That's how wide in frequency space the frequency you're using. And from that, you can tell that the resolution of the radar from just C, T, delta T, the round trip time, is just C over 2 times the bandwidth. Now, one thing you can do is, if you want to get a lot more power on the target, you can make this much longer, the pulse longer. But when you make the pulse longer, you make the bandwidth shorter. And that's going to feed into the resolution, and that that bigger bandwidth makes the resolution smaller. So these two feed against each other. If you've got a good range resolution, you have to have large bandwidth. But large bandwidth gives you very long pulses. So you can use techniques to take a certain time t and compress the waveform, it's called. And you do that by coding this pulse in either phase or frequency. Here, we linearly change the frequency of the pulse from a longer wavelength to a shorter wavelength linearly. And here, what we do is we flip the phase, or don't flip it. And a plus means we keep it at what it is. You get to a minus, and during that sub-interval, you flip the phase 180 degrees. And this is called phase-coded waveforms, binary phase-coded waveforms, because they're just two states. And these are methods that are used to compress the pulse. Spend a whole lecture on it. Now that we've got the data coming in, we can display it in an analog fashion. So if it's like we were looking down on a display of what the radar saw. It transmitted out in this direction, and then these white places are the areas that were above threshold. In this case, the radar had a target right out here, and this was a long exposure photograph, and these sets, if you can see it on your screen, are clearly marked one after the other. That shows the radial motion in or out of the aircraft, because I can't see the time that they were. I can't tell you it was moving in or moving out. These are discrete clutter objects because they don't move. These lines down here are closely spaced towers from high voltage power lines, grids, and they appear to be like a line target, but they don't move. They're there each and every scan. And what we see here is what rain looks like. This is a very heavy rainstorm in the summer of 1975, I think it was, when this was taken. So what we want to do is we'd like to get rid of the rain, get rid of the ground clutter, and if from scan to scan the target moves, but the clutter doesn't move, well, the rain will have some motion, but the ground clutter is not going to move. The first thing that would occur to you is for each time you send a pulse out, you send another pulse out, and for that delay, just subtract the two pulses over the whole range. And a radar A-scope is an oscilloscope that just looks at from time t equals 0 along till the next pulse goes out. And you see, from the ith pulse, you got a certain, either the complex or the imaginary part of the pulse, you get a wavy line. Ith plus 1, you get another wavy line. And you notice that these two places, the amplitude didn't change, because the phase didn't change because of the Doppler effect. And in these two places, they were the same. And here there was a target, and here there was a target. When you subtract them, you get little bumps, which are the results of subtracting two pulses. And this was the first technique that was used. It's called moving target indication, when people didn't have the sophistication of digital signal processing. You can make that digital signal processing just that. That's a form of a high-pass filter. You could make it more sophisticated with 3 pulses or 4 pulses, but it doesn't really do the job, because moving clutter, like this rain, will leak through an MTI filter. So what we wanted to do, what was developed, was using a large number of pulses, the order of 10, process them through a linear filter, and get out a whole series of passband filters. Those 10 backscattered at the same range gate are passed through a set of weights which have a frequency response that of a passband filter or a transversal filter, which has this characteristic. This is one of the 8 or so in this particular processor, and you see that it will detect very well targets going 50 knots, and it'll reject targets going 0 to 20 and 80 to 100. Now, this particular show, the radio velocity is only up to about 110 knots, and that's because, which you'll know if you know from your digital signal processing, the time between pulses wasn't fast enough, and these radio velocities, which transform into Doppler frequency, as we'll see when we look at that in detail, they aliased down. And so when you have many Doppler filters, the rain will alias down into different filters, and if you have a couple of different pulse repetition frequencies, you'll be able to, with these pulse Doppler techniques, be able to track very nicely this, which was a single-engine aircraft, in that rainstorm. It's not the exact same time because this aircraft out here isn't seen. This was taken roughly within minutes of when this test was taken. But this is the radar-only tracking output, and you can see very solid detection of the slow-moving aircraft. These are planes going up and down the East Coast. The test site was at Atlantic City. And the ground clutter is all but disappeared. And this is a road leading away from the test site. You can see some detections from cars leaking through. This is just the time stamp on the output. Now, if you have a whole bank of the filters, this is what will be the output. What I showed you before was just one of the filters. So you get out of the 8 or 10 pulses, you get 8 or 10 outputs, which are all, you look for where you get the threshold crossing in each one of them. And they're adaptively thresholded. We'll get on to all that in detail. Now, this is to show you that adaptive processing is tough. And the reason it's tough is if you look at the clutter, if you have on a radar, on a plane, a rotating antenna, and the main beam is pointed in this direction, which is to be forward, and we have a cruise missile here, this is the target, coming in at you. Here will be the main beam, which will be hitting the ground if it's in front of you at this point, and you'll be, the Doppler of the target is such that you'll be competing against receiver noise. Excuse me. Here, at another angle, the relative Doppler of the clutter has changed. You notice the clutter has spread and has moved in frequency. Here, the same target is tangential, and the clutter has spread a lot and it's embedded in the clutter from the main beam of the radar. This clutter out here on the side is from the side lobes. That's detected from the side lobes of the antenna. And here, the main point is to point out that the Doppler frequency of the main beam clutter depends on the scan direction and the frequency, Doppler frequency of the target depends on the scan direction and the target aspect. We're going to go into this a whole lecture on this. Went through it very quickly. Now, with those detections that we get, we want to correlate the detections that will be several Doppler detections maybe, and several in range, and consolidate them into one target, identify them as having come in one scan of the radar from one individual object. And that's parameter estimation and correlation. Get the best value you know from that scan by the target. And then, and we're going to go into that, the parameter estimation issue in detail in a lecture. And then the tracking issue, which I've shown in this visual, where here the input to the tracker from many different scans. And you see that these targets are coming from one direction and the other, though we'll correlate them not just in range and cross range as they are here. We'll also take time into account, and that makes it much easier to do the tracking. And some of these, like these two little targets here, are in red. They're what we'd call tentative tracks. They didn't make it to the big time, like it's a solid track and it go on your display. And so there'll be a threshold in your tracker process where now it didn't have enough tracks in a row, scans in a row that you saw it, to really call it a track from an actual physical object. So you don't want the false track output to be low. Okay, now we'll move on to transmitters and receivers. We're going to have a section on receivers, how they work at microwave frequencies and in general, and how they're used. But one question that always comes up often is, do you use big tubes to, in one place, generate a huge amount of gain of the small transmitted pulse, and use a traveling wave tube amplifier such as this that has many tens of dB gain? This is an X band, and that kind of a tube is used in the haystack radar, which is huge, well over 100 feet in diameter. And or do you use individual transmit receive modules? And in this PAVE pause radar, you can see they are used, thousands of them, to steer the antenna. It turns out, depending on the application, they both have their place. And we're going to study this whole issue of transmitters and the place of how transmit-receive modules work, and solid-state modules, and tube systems, and the kinds of amplifiers to amplify microwave radiation. All that sort of thing we're going to study in the transmitter-receive section. Now I'll just add, before going on to adaptive processing, that this is the part where there'll be in the rate of view graphs coming of whole talks coming out of the course. There'll be a rate that's going to be reasonably fast. And I'm not sure what that rate is, because I haven't measured what my energy output is going to be. But once you sense, whether it's one lecture a week or one every 2 weeks, they're going to come up through lecture 17 at that rate. Then when I hit lecture 18 and 19, 19 will end what I call the core. I've got to do the view graphs for these next two lectures. I've got a good set of what I want to do, but it's going to take me a while to think through, probably a couple of weeks. I may spend a couple of weeks just doing both lectures. I'm going to be reading a lot and learning a lot to put those two together in a coherent fashion, and then I'll put the PDFs up when I get them, and hopefully you'll quickly tell me any errors before I do the video, any errors in the beam steer, and the just got my eyes were caught to one of the acronyms on the view graph. Then what we'll do is record them, and I'll record them pretty quickly. Then when we move on to that, as I said, I didn't explain to you what adaptive processing was. The goal is that we have an adaptive processing, and I'm going to use one of the two places in radar where we do adaptive signal processing. One is in the time Doppler frequency domain or Doppler velocity domain, and the other is in the linear space across an angle area, and we've got a beam going out, and how can we adaptively weight the phase shifters in that phased array so that we maximize the gain in the direction of the target and minimize the gain in the direction of either clutter or a jammer. They're two separate problems in adaptive processing. We're going to talk about each of them separately, and then there's the field where you bring them all together. And that's called space-time adaptive processing, where you do the huge calculation all at once, and it's particularly useful in airborne radars, and there are books written on it. And I will go over that in the context of our lecture. A whole book is on space-time, 2 or 3 books are on it, and what I would really say is the first great treatise on it by Jim Ward at Lincoln Laboratory on space-time adaptive processing. And then a number of books have followed, and it's always a subject matter in radar conferences, so it's a hot topic of the time. But we're going to study it at the level, a small level, to let you know what it is, at the first-year graduate level, and then you may go on and study it more deeply in your graduate studies or in your industrial work. Lastly, we're going to look at synthetic aperture techniques. And here we see a synthetic aperture image of a golf course. Right here, it's a little hard to see on this image, is you can actually see the flag in the hole. That's the green, and here's I believe a water trap, and then you see the grass around and the trees and cars in a parking lot, and a road here, and this is probably a path down the golf course. These are the shadows from the trees. It's very clear that it looks almost like an optical image. Well, why do you use radar? Well, one reason is optical systems can't see through clouds. Okay? And with enough radar power, you can see great distances that would be hard to see through the atmosphere. But what are the impediments on building just an ordinary radar? Well, you can get very good range resolution. Notice this picture has very good range resolution and cross-range resolution. You know, they're about the same. And you can get very good range resolution by working with very high bandwidth. But angle resolution is tough in the normal processing of a radar signal because it depends on the antenna beam width, and that depends on the size of the antenna. So if you want to map the ground and put an antenna up in an airplane, you're going to be limited with the size of the antenna, and that's going to limit you to fairly wide beam widths. And when you look many tens of miles away, you're going to have a very wide swath in cross range that's your resolution cell, as opposed to relatively small. It's like your area will be a big pancake of resolution. So you want to get that down. Well, the synthetic aperture radar is how you do it. What you do is you have a radar on an airborne platform, and it has an antenna on it, and it illuminates an area on the ground, and the airplane flies, emitting its signal towards that ground path, that same patch in the ground, for a long distance. And then the radar takes and processes the data from that area imaged, all coherently in phase. And when you process that data from here to here, which is a long aperture, it's why it's called synthetic aperture, you get amazing cross-range resolution. And we'll go over the details of how you get it. Now, there are many different ways to do the scanning of a synthetic aperture radar. Here is another one where you do a spotlight here, and then the plane moves a little bit, and this area imaged will move over a little bit more, and a little bit more, and a little bit more,
and you'll get overlapping images as the plane moves. Okay? And then what you have to do is a huge amount of processing, and you'll get an image, and this is called the Spotlight scan mode. There's another mode I won't get into, but I just wanted to point out to you there are different modes, and we're going to get into this in depth in the last of the core lectures. By saying that these two lectures are part of the core, I think you can make a great radar course out of the first two, the first 17 lectures. I want to put these two in because people in universities, particularly that do remote sensing, use synthetic aperture radars a lot to do it. So I scratched my head and I said that needs to be in the core. And secondly, the advent of adaptive processing and signal processing, I felt that that's something that ought to be highlighted in what I'd call a new advanced core radar book. And that's one lecture that I'm putting together. You can buy a whole book about adaptive processing, many, many books of sensors with either sonar or radar adaptive processing. But I wanted to give it in the context of a first-year graduate course, the one lecture status, so they get kind of tagged on at the end. So these last two lectures will come out slower, as I mentioned before. These topics, many of them will be shorter because they're not the basics that I want you to learn real well. They'll use all the stuff in the core, but they're a narrower subject. Okay, and the same way you do synthetic aperture, by moving the radar and having stationary target like that golf green and the flag sticking up, you can take a radar on the ground and it can, from a fixed location, illuminate a rotating body in space or track a body that rotates over a long period in its trajectory. And a very easy way to see how measuring the Doppler at successive periods of time will translate into cross range is if you take and put a large metallic dumbbell in space. Two metallic spheres connected by a rod, let's say is an insulator, doesn't conduct at all. And it's rotating around in the plane. Now, when the radar and the dumbbells, both ends of the dumbbells, are along the same line of sight, there's going to be no radial velocity of either of those objects. But as they move, one will have a positive Doppler and the other will have a negative Doppler. And so if my hand right here is at 0 Doppler, what you'll see in successive Doppler processings of different bunches of pulses is you'll see at the center a big bump from both of them, and then they'll move away and they'll move here. And if you know that it's a rigid body, you can relate the cross range to the Doppler velocity. You will get, and you can put them together, those scattering centers, and if they were all over a 3D object, you could pile it all together and make an image of the object. Now, there are no images of satellites in orbit that are unclassified. But this is a simulated range Doppler image that is very interesting from the contribution that it was able to make. Way back decades ago, the U.S. launched a Skylab satellite that would go up by itself, deploy antenna and solar panels and things like that. And when it got up, they knew something wasn't right, but they didn't know what it was. And so different radars that have very high bandwidth actually measured this satellite that was up in low Earth orbit and came out with an image. Now, this is a simulated image of what a range Doppler image of Skylab would look like, but not the real one. It's simulated. Okay? And I got use of this image from courtesy of Lincoln Laboratory. So you can tell clearly that these panels, it was all in one big cylinder in the missile, and they deployed fine, but one of these big solar panels clearly didn't deploy. And apparently, the image gave NASA enough information that, metaphorically speaking, when the astronauts went up to land and dock, with Skylab, they knew what tools to bring with them so that they could manually, on spacewalks, make the solar panel, go out and work, and they could do their stuff. And that it was truly a very useful way where synthetic aperture imaging of Skylab, when it first went up, allowed the Skylab missions to follow with men in them to be very successful and do a lot of science and different things from space. And we'll go look more into synthetic aperture radar and how it works, certainly in the course. But this is a nice one-panel view graph. Okay, electronic countermeasures. There are two kinds, really. They're the kind, this is a World War II photo of chaff, they called it window then, being dropped by bombers. So this would obscure the bomber formations from German aircraft, interceptors that had radars in them, and ground-based radars, so they couldn't see exactly where the bomber formations were to attack them and knock them down. And that's called a passive jamming. That can be active jamming, where you can have a plane with a huge transmitter transmit energy towards the radar. And this would be the radar being jammed, because this signal from another location will put a huge signal in the side lobes of the antenna and hopefully lower the signal-to-noise ratio so that the aircraft can't be detected. And that's one reason we want to put nulls in the side lobes of the directions of the jammer. And that's, I think, that's what I've said in these words. Okay? Now, as I go on with subjects I've given a lecture in jammers. I've never done one on this. It took me about 20 years to get to the point where I knew enough about all the different parts of radars that if you gave me a set of performance requirements, I could sit down and say, well, with all these different performance criteria and constraints, cost being a big one, you could meet the operational requirements of the radar with all these constraints. It's almost like a giant nonlinear equation you want to solve. It's sometimes not linear, but it's got constraints on it to constrain and people who do that are radar synthesizers. And I'm going to make an attempt, after having learned that technique, at how one would go about this in a rational way, as best I can. And it's sort of a problem for me. And what I get together that I think would teach other people how to do that, I'm going to put together in a lecture. So we'll talk, I don't know what's going to evolve, but I'm going to try and do that. Okay? Next thing I'd like to talk about is an advance that hasn't been taken completely openly by the whole world out there, but eventually is really going to. Traditional radar system architectures are built where you have a main computer, and they connect up to a big custom box of proprietary interfaces from the computer out to the receiver, exciter, the waveform generator, antenna controller, signal processor, and just bits are flowing back and forth, bits. And these are built with, a lot of times, with very custom-made equipment, expensive. And these radars, where the antenna and receiver are on the other side, are very hard to debug because there are bits flying back and forth, and you don't know. at the bit level in real-time systems, it's very hard to debug one piece and know it's not the other pieces interacting. The radar systems open systems architecture was developed at Lincoln Laboratory. Steve Rado gets the kudos for that idea, and he, in designing a radar that we've developed at the laboratory, the first one, Cobra Gemini radar, he felt the best way to do this was to have all these different subsystems. First of all, absolutely minimize the use of custom hardware. And in the first generation, Rosa, I think there was maybe one or two or three COTS boards in all of these subsystems, and to have a separate rack for each subsystem, and all the other boards be off the shelf. You can get anywhere in the country, like you can go, and that the interfaces be all off the shelf with a common Ethernet. The most important thing is that, and all industry standard interfaces. The most important thing is the exciter, receiver, antenna controller, and signal processor and whatever would send high-level messages to the main computer that did the tracking. Like the main computer would say, point the antenna at a range of this and an azimuth of this. The main computer wouldn't take part in the servo mechanisms. All that stuff would be handled in the antenna controller. And when you do that, you can debug each of these systems isolated with a simulator, simulating the main controller, the main computer, which would have displays and do the number crunching, so that you can develop the system in parallel. And that way, when you get one system, subsystem, like the receiver subsystem working, and you can exciter, signal processor, antenna controller, the main controller knows what it accepts, high order messages, and you can debug a whole radar system in orders of magnitude less time, save huge amounts of time. And that we found at Lincoln Laboratory has been a very fruitful way to modify different radars. And it's being picked up slowly but surely by industry. But I'm going to give you a lecture on that. It probably isn't the most up-to-date because I've been retired for a fair amount of years, but it'll give you a beginnings of it. Okay? Next is over-the-horizon radars. I always like to talk about over-the-horizon radars because I actually worked on one back in the 1970s on data from one when I was at the MITRE Corporation. It was the radar that was built for Maine for air defense. And also I'm an amateur radio operator, which is a communications system. It uses the ionosphere, and it's between these wavelengths. So I know about the ionosphere. The ionosphere, the frequencies that over-the-horizon radars work at are very, very different than microwave frequencies, in that they don't just go up and over and look into space, but when they hit the ionosphere, they bend down and hit the Earth. So they'll have a big clutter problem. And at these wavelengths that the ionosphere works and does this, it's typically 10 to 80 meters in wavelength. And so that this gives them the opportunity to detect targets truly that are at very long ranges, aircraft and ships in the order of 2,000 miles and from the ground. And here's an example of one over-the-horizon radar. It's a bistatic system. And this is the relocatable OTH radar, Rother. It's its acronym. It was made by Raytheon. And I'll talk about that whole technology and a lot of what I think and know about it and stuff like that, having worked and played with the ionosphere a long time. Next are weather radars. Here's the WSR-88, affectionately known as NEXTRAD. And here's NOAA output of Hurricane Bertha in 1996. You can easily see what it's doing in units of dBz, which are intensity. You probably can't read the dBz units. It's color-coded. It shows you the eye of a hurricane. This is a repeating GIF file from Wilmington, North Carolina, as the eye comes ashore right there into North Carolina. And if you're interested, you can go to their website, hit NOAA, NEXTRAD, and see gazillions of these. And we'll talk about what frequency it is and how it works and stuff like that. And next we're going to look about space-based remote sensing radars. This radar was built by Jet Propulsion Laboratory. It's on a spacecraft. And the spacecraft flew out to Venus and mapped Venus with a synthetic aperture radar. Here we see the antenna. And gave fantastic science on. So we're going to talk about space-based remote sensing radars and just go over a few things which I'm going to learn about. I'm frankly right now quite ignorant about it. So I'll spend some time learning about it and put this up so people will be able to see it as one of the uses. Air traffic control for decades and decades, and civilians have used radars. The meat and potatoes of air traffic control radars are the hundreds of aircraft surveillance radars that see out to 60 miles, everything from a small Piper Cherokee to a big 707, and they're located around all the major airports in the country. And these long-range ARSR, this is an ARSR-4 that was made by Northrop Grumman. It is an array-fed reflector. This is a hybrid array. We're going to take a look at that. And these are ASDI radars. I believe this is an ASDI-4 on a control tower. It spins around fast. I think it's a K-band, one of the millimeter wave frequencies, I think. And it looks at the ground traffic. And so one plane using one way doesn't, get in the wrong direction, and we have a fender bender that kills 200 people. Many hundreds of people as one plane is taking off, goes into another plane crossing the runway. A real disaster. In the Azores, you remember that terrible disaster that happened. Also, what do I call this? This is hard to call it a boat or a ship. A lot of boats and a lot of ships all have radars that look at other ships and buoys which have corner reflectors on them so they can navigate at night and in the fog. I was hesitating because this is probably, it could be a 50-foot luxury ship, not 50, 100, 150-foot luxury ship. But a lot of people with much more modest sailboats will have a radar on them. Now, next to ground-penetrating radars. I would say up until the Iraq War, the second Iraq War, the only people that used ground-penetrating radars, well, they were used in Vietnam to look for caves for the Viet Cong, way back in the Vietnam War to some extent in the latter stages. But a lot of people that have used them since the end of that war have been people like these two people who are exploring a burial ground, doing archaeology and looking for archaeological artifacts in the ground. And here we see the output from, here's a fellow with the controller, and it'll have a display that would look something like that. These are images from a Flickr, and here's a fellow with the ground-penetrating radar. They operate at very long wavelengths because ground has very high attenuation, and those wavelengths it works best at. And you can see the returns from some buried objects in the ground. And this is a burial ground, so you don't know exactly whether it's coffins or artifacts from an archaeological dig or whatever. Then there's the whole class I alluded to of range instrumentation radars, and I'll go over what they do, how they do, why they do it, at what frequency, and we'll talk about the characteristics of many range instrumentation radars that NASA and the government uses to be scorekeeper, so to speak. And lastly, military systems. This is a subject that's of great interest, obviously, to everyone in the military, but it's a curiosity and an interest, I think, of everyone in the world. And there's a reasonable amount that's put out, that's in the open media, about different systems. Here's a counter battery radar that was built by a Raytheon subsidiary, or Raytheon, and originally they were built by Hughes. And here's a military aircraft detection and surveillance and tracking radar for relatively short ranges that Raytheon built. Here's the Aegis radar is built, half of it's built by Lockheed Martin. The antennas and the signal processors and the transmitters are built by a Raytheon on an Aegis destroyer. They're on our whole fleet of cruisers too. And here's in one of our modern jet fighters in the nose, a slotted antenna for an airborne radar. And the Joint Stars radar is located here. Here's one of the radars in the Soviet air defense system since the downfall of the Soviet Union. The Soviet Union's done a lot of bringing their systems out to sell them to other countries, and they put them on parade at openly market them at air shows. And this is one that was from Wikimedia. There's a gentleman that I've found out from the web who's taken some fantastic pictures of Soviet air defense radars, and found a great article that was transmitted to me that was in a European open journal on the history of Soviet air defense radars up to the now. And the author was kind enough to send me all the JPEGs, and so I'm going to be using that as a source of some descriptions of some of their stuff. Just like everyone, they don't, in the radar equation, you can see there's about 9 parameters that really specify a radar. And what will happen is you'll never hear anything told about the signal processor or the exact waveforms or the exact cross-section at what range it can detect. They'll tell you the class it can, So they grew it up enough so that you can tell something about it, but they're not going to give away their national defense secrets. No one is going to do that. And certainly I wouldn't go near the edge of that cliff. But again, let's just some interest of some of the things in military systems and how they've developed. Actually, one thing I want to add at this point, as I go through the whole radar system, the description of radar, I include a lot of non-state-of-the-art radar techniques. Because when we put a radar out there in the field, we don't just put it out there on a system. We don't put that radar out for 5 years and then we just get rid of the radar, put a new one in. They're too expensive. We do upgrades to the radars when they're needed, and some of the systems in operational radars in our air traffic control system are things that you'd never today build in an air traffic control system. But since they're out there in the field, operated, I think it's useful to teach about them and teach enough so that people will know the techniques that are antiquated in terms of state-of-the-art or what the military would use. But if you really want to build a low-cost radar for civilian use, that might be a technique you'd want to use. So, problems. Yes, we're going to have problems for every lecture and even for this introduction. These are a couple of simple problems you ought to be able to figure out for yourself very easily. I like the last one. I'll even read it to you. You're going 75 miles an hour in your new bright red Ferrari. The policeman, state trooper, uses his handheld X-band speed radar, clocks you, and he says, "Uh-oh, this guy's going too fast." And assuming you're going 75 miles an hour and it's an X-band radar, and you're speeding toward his strap, how many hertz is this 9200 hertz shifted by the Doppler effect, and is it positive or negative? A little cutesy stuff to it. The others are sort of simple problems to start you off. Believe me, the ones coming up won't be. And to summarize things, hope you have as good luck as I'm having putting this together, and I hope We're going to cover an awful lot of ground. This is not a course for children. It's like crammed into this size, and these topics are not everything I know, but what I can put in this many view graphs for a graduate course. There's a lot of stuff I know that's beyond that, and there are some places in this that I'm a little weak. But and I'm going to have to get myself in good shape for, because I'm not Mr. Answer Man of everything about radar. And so in the next two topics, they're going to be very quick reviews of what you need to know in these subjects. But don't be forlorn if you don't get everything when you snap through these lectures. I'm going to give you references on where you can look on the web to take courses in these subjects, video courses. I know there's some really good courses in signals and systems and digital signal processing that are on the Berkeley website. And there's a course with notes in electromagnetics down at MIT's OpenCourseWare. And I'm going to be searching the web for a video course for that lecture so that you can, on your own. The one thing I will add, very easy texts, and I'm going to turn just for a minute to see if I could drag one out. I can't seem to find one. The Schwab series on signals and systems, digital signal processing, are very quick and easy ways to pick up they're like cliff notes on digital signal processing and signals and systems. So you can get through them real quickly and easily and understand the things that you need to do. And in electromagnetics, particularly in an E&M course, the physicists will study electrostatics a lot. They won't study transmission lines, impedance. The double E's will study impedance in transmission lines, won't spend much time on electrostatics. In the things I point out to you are the subsets of all of electromagnetism that you're going to need to know. So you don't have to go through everything, but know the things that I touch on in these lectures. So good luck to you all on this journey, and I hope at the end of it it'll make a real difference to your professional development, and hopefully after I get through the core of the course, we'll be developing a relationship with the university so that students can take the course online and through distance learning, have a recitation section, and we can go back and forth with questions. And the mechanics of that, I'm getting way ahead of myself when I talk about the logistics of how that's done. I've been talking with a couple of universities. They are very interested in having that kind of a dynamic set up. And good luck to you all. And I hope you enjoy doing this as taking the course. I know it's been a lot of hard work putting this one particularly together. I really enjoyed putting together the first course, and a lot of people watched it, so it must have done some value. This is again one time I'll implore you, please let me know if there's anything wrong in this course, or there's a piece of the lecture that you just don't get, and you've got the background to understand it. Then what I'll do is in time, because I'm going to try to rush to get as fast as prudently possible, I'm going to rush to get the core done, and then I'm going to go back and redo stuff. And since it's in little bite-sized pieces, I can review the bite-sized pieces. Anyway, let's see if there are any more view graphs. If there aren't, sayonara. There is. Okay, here are the references. I first of all want to go back. I did not, in the next lecture, I'll put it on successively. Here's another new book, an introduction. If I were doing this view graph over, it's the one, Principles of Modern Radar by Mark Richards et al. I put that as the second instead of Fred Nathanson's for the elementary stuff. General Toomey's book, he was a general. This is a very, very, very basic book for the non-specialist. Bob Uderi has a great book about the evolution of radar and how it affected World War II. And I had a lot of fun reading that. There's Professor Levinen's book on radar principles, all equations, not many pictures of hardware, and Uli's book in Fundamentals of Applied Math. And I'd also add, for the physicists, Ray would have taken Griffith's book, which I have back here. I won't turn my head and waste your time, but Griffith's on electromagnetism. That tends to be the book that physicists take their junior year, and it's the equivalent of this book by Uliby that electrical engineers take their junior year, which would be great going into the next lecture. You'll do a lot. So take care. Have a great day.